Let's start this. Okay. In that case, let me throw up the screen. And we will start working on part 2 of this problem. Okay. So you should be able to see my Atom editor right now. And let's quickly kind of recap what we did on Monday. On Monday, we went ahead and built out the slave device for our I2C module. Remember, the slave device, different from the slave device in the SPI interface, where the SPI interface slave device is looking for that slave select signal to see if it runs. Here, this guy is just listening for its address. And once it does that, like once it hears its address, it puts out data. So I saw some people talking on the chat wondering about like what is the master sending versus what is the slave receiving, right? And someone put it pretty great, which is, you know, the master just sends the address, right? And all the slave does is listen to those address bits coming out, and when all 8 bits are done, we sort of stop and say, hey, you know, was the address that we received equal to our address? And if they are, then we respond by sending out the data at those positive edge signals. Let's go ahead and run it. Let's see. In fact, we can actually skip over some stuff. GTK wave. Actually, we can run the simulation. VBP s device.vbp. GTK wave s underscore device dot VCD. And there we see an output kind of similar. It goes in reverse direction from the one from the assignment, but we can see that the receivers were getting addresses all on the same line, and then each slave device responded with its data in kind. And all 4 of them worked as they were supposed to. Does anyone have any questions about the slave device stuff that we did last time before we move on and make the master device? Okay, in that case, let's get to it. Clear this out. All right, so the master device needs to send the address out and then listen for the data coming back in. So what we need is, first we're going to need to create an address to store that data. So we'll create reg data. This is, I believe, just like the one in y'all's assignment, reg data. And then, let's see. We're going to need an input that looks for the address, right? This is the outside world saying, hey, go look for this data. So we'll have input address. That address is going to be 8 bits, 7 to 0, ADDR. And then what we'll do here is we'll say always at posit, or not posit, what am I saying? Always at address. So what this means is that anytime that address input changes, this section will execute. So begin and end. Now inside that, what do we need to do? We need to pulse the clock, and then we need to push for the first 8 bits, we need to push, and for the last 8 bits, we need to read. So we're going to kind of do the same thing we did last time, right? Let's go ahead and do create an integer I, set it equal to 0, and then we need to pulse the clock. So here we're going to do something kind of strange, so make sure you're paying attention to this. We're going to set the clock equal to 0, and then, because again it's not a programming language and the timing is kind of strange, what I actually want to do is implement a delay just like we see in our test benches. Now, up till now, we've only ever used these delays in our test benches, but we can use them here in our Verilog code. For my EEs, my computer engineers, this will not work on an FPGA, right? When you get to lab 1 and you got to use the basis board to program your robot, you can't do this. This only works in a simulated environment, so keep that in mind. Here you'll be governed by the actual system clock, but that's a whole different thing. But to make that work, we need to define what that is. So we actually need to create a timescale statement here in this Verilog file, so that this Verilog file knows what that means. So we're going to do it like this so that it's in sync with kind of what we've been working with this entire time. So we're going to set the clock equal to 0. And then, let's see. Oh, actually, we're going to wrap that in a for loop because we want to do this 8 times. So I'm actually going to cut that for just a second. Say for I equals 0, I less than 8, and I equals I plus 1. Begin and end. Now we'll set the clock equal to 0. Now all we'll do is say, remember, the address we were given is the address for the slave device that we want to go pull from. So this is what we're going to read from. So what we'll do is now we'll say that tx is equal to addr I. So we'll set that, and then we'll pulse the clock one more time. We'll say clock, or now we'll go clock equals 1. This gives us that rising edge. So we're essentially saying set the clock to 0, wait a second, update the new value of our output transmitter, then set clock to 1 to cause that rising edge. Basically what we're doing here, when we set this to 1, this is going to create that pause edge clock for our slave devices. And that's all we need to do in this for loop, I believe. And then now what we're going to do next is read. The master device is kind of easier because it controls the clock. So we have a lot of control over what's going to happen. So instead of having to do counters, which wasn't that difficult, here we can just keep doing for loops. I equals I plus 1. Begin and end. Now remember the process, in fact, the code for this master device is going to be almost exactly the same for the SPI device. You know, you're just going to be doing some chip select stuff at the top. All right, now here's the next 8 pulses of the clock. So we still need to make sure we're driving the clock. So we'll do clock equals 0 to give us that low edge. We'll delay for 10 nanoseconds. We'll do clock equals 1. Delay for 10 nanoseconds. And in the in-between time, ooh, actually, I take that back. We can't put this in here because that won't necessarily work. Remember, because the slave device is only going to give us bits on the rising edge. So what we're actually going to do here is do 0, 1, and then read. So we'll say data. Now we want to store the data. The data at bit I is equal to Rx. And so for 8 pulses of the clock, we'll go ahead and read some data. So here we go. I think that's everything that we need to do. So we did a for loop for 8 clock pulses. Set the clock to 0, write one of our address bits, set the clock to 1 to force that positive edge. And then for 8 more, now we're on the read side, create a rising edge, and then read what this is, right? So this is going to correspond to after the pause edge of the clock, get that data from the slave device. So I think that's it. Are there any questions about what we've written here before we dive into the test bench? All right then. So let's go ahead and create a test bench. We'll do this one as like an overarching test bench. So we'll just call it testbench.v. And we need to do some of our boilerplate stuff. We need a timescale, 1 nanosecond, 1 nanosecond. We need to include our starter.v file. Oh, it needs to be in parentheses. And now we have module test bench end module. All right, now we need some stuff. We need registers for our inputs. So we need that 7 to 0 adder, then reg. Let's see what's going to happen here. Actually, that's all we need for that. And I don't think we need any output. We're just going to read this data. Okay. So I'm kind of thinking in real time about the best way to wrap this up. So the transmit is going to be a wire. Okay, we got this figured out. So I'm going to leave that for just now, and we're going to go and implement our modules, and then we'll kind of put it together as we need to. So what we're going to have is a master device, which we'll call UT master 0, open these close parentheses, and then we'll have 4 slave devices, UT S0, open close, UT S1, UT S0, semicolon, not a regular colon, not slave 0, slave 2, slave device UT S3. Okay, so let's see. For the master device, we're going to have adder connected to adder. That's our controllable bit. Then it's TX. In fact, so we're going to create a wire. In fact, let's call this wire Mosey. So it's TX will be attached to Mosey. Remember, master out, slave in. It's RX. Let's create another wire. We can call it meso, master in, slave out. Now we're sort of crossing terminologies a little bit. And it's clock. Let's create a wire, and let's just go ahead and call it S clock. Now, oh, I remember everything got weird here. We're gonna need to change that. Okay. So for the slave devices, we're gonna need, what do we have? RX, TX, and clock. So its .tx would be Mosey. Its RX would be, so it's receiving, wait, no. Its transmitter would be master in, slave out would be meso. Its RX would be Mosey. And its clock would be our S clock. Right there. Now, we're going to repeat basically all of this again. Meso .rx is Mosey. .clock is S clock. If I can speed things up, let's just go ahead and copy and paste. Now we have a little bit of a problem. If we tried to run this, well, once we add our stuff, if we tried to run this, having all of these meso wires attached to the single receiver will actually cause the simulator to throw an error. You can't have one signal driven by multiple independent signals. So what we're going to do instead is we're going to create an intermediary wire. We'll call it wire underscore meso, and it needs to be 4 bits. And what we'll do is we'll replace each of these guys with wire meso 0, 1, 2, and 3. 1, 2, 3. And what we'll do is we'll assign the actual wire meso equal to the OR-ing of all of the wire mesos. And basically what this does is, remember an OR gate, we talked about this in classes, is a way to kind of cheat and bring a bunch of different signals onto one line. That's kind of what we're doing here. Since we know that only one slave device should be talking at a time, we can OR each of these signals together and get just basically one signal at a time will talk. They shouldn't talk over each other. So that's just a weird sort of hacky step that we need to do. Now let's go ahead and do the cool stuff. Initial begin and end. Let's go back to this other test bench just to kind of get a sense of what we did. So we're going to need to create some stuff. Okay. So these guys need to know what their addresses are. So I'm going to copy and paste that. Actually, before I do that, let me go ahead and create my files. Dump file 0, and we'll call this, actually let's call this I2C, I2C dot VCD. And the dump vars are equal to, get stuff backwards, it's been a long day, 0 test bench. Now let's go ahead and we're going to copy this stuff. Right, remember this initializes those values in our slave devices. So what we'll do here is, remember, we'll set S0, S1, S2, S3, and S3. Okay. Now, what do we want to do? So basically all we're going to do is we're going to set the address, and that should kick off the event. So what we'll do is we're going to say that our signal ADDR, let's first set it equal to just the first slave device's address. I think that won't cause any problems. And then we just need to wait for a little while. And on the test bench that we did, it found out that waiting for like 500 nanoseconds was enough time to see everything happen. So this should let us view the first result. Actually, there's no reason not to do the whole thing. So 2, 3, 4. So we're going to cycle through S1, S2, and S3, setting the addresses. Setting that address should kick off this action in the master device module, and we should get some good stuff. So now let's go ahead. Well, actually, before we run the test bench, are there any questions about what we've written so far? Okay, well, let's run it and see if we screw anything up. Okay, Verilog, option O, let's just do this. Test bench dot VBP from tests / testbench.v, and let's see what happens. Oh yeah, all kinds of good stuff. All right. So let's see, error 23, 13, 24, 13, 25, 13, 30, 15. Okay, so it really did not like me trying to assign the clock to that guy. So let's see, where is that happening? Oh, not my test bench. Okay, so let's go ahead and take a look at where we screwed this up. Ah, I see. Okay. We actually made this mistake last time, I think. Remember, since we're updating these guys inside a sequential logic block, right? Always, since we're inside an always at block, these guys need to be regs. All right. And see, that's basically what's going here. 13, 13, 13, 13. It was saying, hey, these guys are wires. You can't do that. It's all wrong. All right. So now let's go ahead and run the simulator again, see if anything happens. All right, more bad stuff. Let's see. Starter 13 and 14 invalid. Variable list in port declaration. And starter 13 and 14. Orange TX. So what is your deal? Oh, I used a comma, not a semicolon. Maybe that's it. It's always something dumb like that. Hey, there we go. All right, so now we'll go ahead and do VBP I2C dot VBP. All right, and nothing broke, so let's go ahead and run GTK wave I2C dot VCD. And we'll see if good stuff happened. All right, let's go ahead and look at that. Pinned. Ooh, that's weird. Okay, so some stuff is messed up. Let's see. Well, we've got meso. So let's see. Some stuff is working, right? Address is working. The S clock seems to be working properly. The MOSI, master out slave in, seems to be working properly, except it looks like I have these two variables here. I called something SCKL. I typoed up serial clock in some place. So let's go ahead and take a look back at the code and see where we screwed that up. Yeah, at every time. S clock. I'm surprised it didn't throw an error when I did that. All right. Let's try it all again. VP. Get the GTK wave. Now let's grab all the stuff. There's one fewer signal. Pop it open. Pop the thing. Okay, so it's still not working, but it's not all bad. All right, let's take a look at the meso wire. Oh, yeah. Okay, so it looks like some things are working. The output from MOSI seems to be working just fine. It seems like the meso lines are working properly. Oh, maybe I should go ahead and let's see. Add or equal 0. Wire meso, sign meso. I'm going to do this. I'm going to set these registers equal to 0 to try to clean up some of this output just a little bit. Try to get rid of some of that red. Especially when there's lots of red, you want to sort of isolate where that red is coming from. Okay, so we've got a lot of, oh, actually, hold on. A lot of stuff got fixed. What is going on? I guess let's take a look at data and see what is going on. So let's go ahead and grab the data register, pin that guy. Okay, so it still seems like some screwy stuff is happening. What is the address? What is the data at each of these guys? 5D. That's one. That's two. So I'm just pinning all the data lines so I can read and see what they are. Actually, I think it's working just fine. We were all worried for nothing. Okay, so let's see. Actually, this guy seems to be working. Now I know it probably this looks way superior than the SPY one. And the biggest take home is notice that the data lines kind of get weird before they sort of lock into the values, right? So the value for the value of data for the first slave device was 5D in hex, right? And it wasn't until the very end here that it's not until the last clock pulse, right, that it locks into that value. And the reason for that is pretty simple, right? It's the bits are changing until all the way. So if we go back to the Verilog code, right, we're just pushing new data into that data register. So it sort of makes sense that while those bits are changing, these values are constantly changing. The actual overall value of data is changing until the very end, and it's like, okay, it's got the number that it wants. So here it changes in a couple places, and then it's got the right data, and here it changes a whole bunch of times, and then it's on the very last pulse that it's got the correct data, right? 4-1 from this guy, 4-1, and 6C from the last one. Okay, so that means that this guy is working. The meso line looks weird, freaks me out, but I guess it's doing what it's supposed to. Oh, it's because meso is trying to. So the wire meso line looks super weird up here because it's trying to interpret 4 bits of number, right? Even though we're treating it as just one serial line split 4 ways. Okay, so I think that is it working properly. which means that we have done everything that we need to do. We've completed the assignment, if this were an assignment. And now you should know everything you need to know in order to complete the SPY assignment, right? And this is a pretty, if you can write a serial interface in Verilog, you're allowed to go home and say, yeah, I know how to code in Verilog. Trying to think, let's recap a little bit. There wasn't a whole lot here, right? Anytime the address input changed, set the clock to 0, push some bits out, set the clock to 1 to create a positive edge, do that 8 times, and then for 8 more times, cycle the clock, and check out what data we received and go ahead and store that in the appropriate place, and you are good to go. All right, so that is it for developing a I2C interface in Verilog. That didn't take nearly as long as I thought it would. So what questions do you guys have about this or about the other assignment or anything? Don't forget that you can type something in the chat, or if you want to talk, don't forget everyone is set to push to talk. So.
Yeah, could you relate some of the values for this interface and kind of compare it to like what we're working on? Because I wasn't there for the first meeting. Still need to watch the video, but like what TX means and RX means.
Okay.
Relative to the other one.
So first thing, definitely go back and watch the other video because we explained a lot of that stuff in the other video, or on Monday's video. But basically what's going on here is, so the terms in SPY, right? Let me do a comment, right? There's MOSI, which stands for master in, slave out. There's MISO, which stands for, excuse me, I got that totally backwards because I was thinking of the next one. Master out, slave in. Sorry about that. There's MISO, which is master in, slave out. And then there's S clock, which is just the serial clock. Now, in your solution, right, in SPY, we use these names for everything. In I2C, we don't use these names. But basically, you can think of MOSI as the master out going into the slave. So up here, for the master, TX, the transmitter is MOSI. So the master device transmits, so it's master out to the slaves, slave in. And then RX is what it receives from the slave devices, master in, slave out. And then clock is equal to, S clock. That one's pretty simple. And then on the other side, it basically flips over. And down here we have that here, the TX, what the slave device is receiving, is the master in, slave out. The RX is what the slave device is receiving, so the master out, slave in. And then its clock is still just the S clock. Notice that for the master device, the clock is an output, and for the slave device, the clock is an input. So did that answer your question, Gordon?
Yes, it does.
Cool. Okay, Zach asks, in the final project, S clock and MOSI are not declared as reg, so when I try to change S clock, it brings up the error that is not a valid value. Are we supposed to create a new reg values to use as the S clock? I think maybe I made a mistake by putting like do not modify all over the place. You can go back and add, so S clock and MOSI need to be regis. So just add those to those lines. So go back up to that line in your starter file and just make sure that all your outputs are listed as regis. I mean, as you can see, I forgot to do it here when we were doing this in real time. I suppose I probably just forgot to do it before I shipped out the starter file. But yeah, go ahead and don't forget to add those regis right there for all of your outputs. Okay, what else?
Do inputs need to be regis as well, or just the outputs?
Just the outputs.
Cool. Thank you.
Yeah, no problem. What else? Okay, if there are no other questions, I guess we'll call it a day early. Even though we've finished with this whole thing, we'll still do another office hour session on Friday. Just so you guys who are working on the assignment can ask some more questions and get some more help if you need it. But from this point, as long as if you've been here both today and on Monday, or if you've watched the videos, you know everything that you need to know in order to get this assignment done. You just got to maybe, do some thinking to figure out how it's going to work. Remember, the real big difference is you have to sort of incorporate that slave select into the master and slave device. It's really the only fundamental difference. The master device is still going to ask for an address just like it does in I2C. And it's going to read that data just like it does in I2C. So like I said, the master, with the exception of adding that slave select, in this code you could almost just like copy and paste pretty much. Minimal tweaking. So yeah, so if there's nothing else, thank you so much for hanging out with me. This was kind of a fun thing to code. I had never done an I2C interface in Verilog before, so this was pretty fun for me. And yeah, feel free to shoot me an email if you have need any more help. And if not, I'll see you guys later or talk to you on Friday. Thanks, y'all.